Hi all, in this video we shall understand the working of self-attention mechanism in transformers. Basically, many of you have been asking that how transformer architecture works, if we could implement the transformer architecture. So step by step we shall first understand the need for self-attention mechanism, what is self-attention, and then we shall implement the self-attention mechanism in Python. Okay, so let us go step by step and understand the need for self-attention. So before the advent of transformer based models, sequence modeling or NLP based tasks was performed using RNN architecture, RNNs or recurrent neural networks. Okay, these recurrent neural networks can perform sequential processing, which means they accept a token one by one. For example, our input is data science learning is fun. So at time step t minus 1, say we are processing data, right? Then in the next time step t we shall process science, so on and so forth. So this goes in a sequential manner. At any given time step we have only one input token. Okay, so this is what sequential processing is about. This sequential processing dealt with various challenges. Some of these challenges included the long term dependencies are vanished, which means if say for example the sequence length is long, the tokens that appear at a later point, say fun, and the token that appear earlier, say data, the dependency between them is vanished if there is any. Okay, the other challenge was that tokens that appear later are not able to contribute. So say for example when we are working with this word science, right? So when we are working with science, when we are preparing the context vector for science, we have no idea about the remaining tokens. Learning is fun, we don't know about them. So therefore we only know the token that came prior to it and the current token, and the tokens that came later are not able to contribute to the context. And the third was that this is primarily a sequential processing, so there is very little scope for parallelization. So from computational standpoint there are additional challenges. Some of these challenges have been dealt with LSTMs and GRUs, which use GRU is basically gated recurrent neural network, recurrent unit. Okay, so it tried to deal with the long term dependencies by using gating features, only preserving the most important information. However, there were dependencies in terms of the tokens that are appearing later, so the sequential processing. Again, in BiLSTMs we try to process and deal with the challenge of tokens that appear later to be included in the context. But see how BiLSTMs used to work. See, I have a diagram here for BiLSTM. So BiLSTM basically combines two LSTMs or two sequences. One is the forward pass, other is the backward pass. However, in any given sequence, say data science is fun. So when you are processing them this way, you would have knowledge of the tokens that appear on the left side, and when you are processing in the reverse manner, you have knowledge of the tokens that appear on the right side. At any given point, a given token would not have knowledge of both its forward as well as backward tokens. So this is missing, and therefore there is some loss in preserving the actual context. So now with the transformer based models we introduce self attention, which makes it very powerful. And the way self attention works is, self attention allows the entire input to be passed at once. So you are looking at the entire input sequence at once, and therefore the context can be prepared using both the tokens that appear earlier as well as tokens that appear later. Let us understand them using the diagram. So here you see I have taken a basic example, data science learning is fun. So a matrix is generated, basically a self attention matrix, where you have in the rows you have the same tokens as well as in the columns you have the same tokens, and a mapping between any two token is the attention or the score of attention for a particular input based on the other inputs. Okay, so this is the score corresponding to science for data. Okay, this is how self attention. This is just a basic diagram to help you understand. We shall deep dive into the components of the architecture. Okay, the components of the self attention mechanism. Let us understand where self attention is used within the transformer architecture. So you know this is the transformer architecture. Okay, just a second. Yeah, so this is the transformer architecture. This is the encoder and this is the decoder. Encoder, decoder. Okay, so now in these two components you see multi-head attention. Okay, So these multi-head attentions are nothing but self-attention mechanisms that are added over multiple layers. Okay, so basically each of these self-attention layers would learn a unique feature for that particular matrix, okay, for that particular input sequence. Now in this video we are going to learn about self-attention. So what we shall do, we shall dive deeper into the self-attention and what are the various components of self-attention. Okay, self-attention makes the transformer models powerful, we already know that, enables generating context based on the entire sequence. Now let us see the operations in self-attention. So basically self-attention comprises of three primary components, Q, K and V. Q is the matrix of query vectors, K is the matrix of key vectors and V is the matrix of value vectors. Now what these three denote, will come to the mathematical computation in a while. Let's see what these denote. So Q is basically what am I looking for. Say when you are going for a YouTube search, okay, so in YouTube search you give the keyword Datahat. Now Datahat is the query that you are looking for. What you are looking for is Datahat. Now against the algorithm will go back into its database and look against all the videos that are possible, look for their tags, look for their titles, look for the descriptions. So all those other videos which the algorithm can offer form the keys or K, okay. So each of these vectors will be K or key vectors, and values are basically the weights associated with each of those vectors. So what value can I offer? So this is what query, key and vector value represent. Hope you understand Q, K and V, their basic analogies, what they try to depict. Now next we shall see the mathematical computation. So in the mathematical computation you see how we generate this Q, K and V. So basically this Q vector is generated from the embeddings, input embeddings and a vector or a matrix WQ. So WQ is learned during training. Similarly we have a matrix WK and we have WV, and some of the other notations that you need to know is L. This is the sequence length, okay. We have L, we have what we say, let's say length of the key or the basically the dimensions of this key vector, okay, key dimension, and then we have LV, dimensions of value vector. When we go basically we also represent it as DK, okay, DK and DV, not LK, okay, that was my mistake, sorry. LK and LV we represent in another notation, but DK and DV. So you see here we have three matrices Q, K and V. Between Q and K we have a matrix multiplication. So we have Q dot KT, we take a transpose because Q matrix will have the dimensions L cross DK and K matrix will also have L cross DK, okay. So we take a transpose, let me write here, so L cross DK and L cross DK. So when we take a transpose this will be DK cross L, okay. And you know in matrix multiplication the rows of the first and the columns of the second are the dimensions of your output matrix, so it is L cross L, okay. We'll see when we go to the notebook and the implementation, okay. Next what we do, we scale them. Why? Because when we compute these matrices it might so happen that the scale or the variance of the outputs of these vectors grow much larger in proportion compared to their original matrices. So that is why we just scale them using a constant. Then we mask them. This masking is optional and it is used primarily in decoder. We are not going into the deeper part of it. I'll tell you when the need comes, okay. Next we apply the softmax and again the matrix multiplication between the output of this and the value vector. Let me write the formula and help you understand here, okay. You see formula is here. So attention is basically softmax of Q dot KT and then we scale it using root of DK, do the softmax and then multiply matrix multiplication with V, okay. So basically the output of this will be L cross L and then V will be L cross DV, So the final output we will have is L cross dV. Okay, this is our final output of the attention. Okay, now we shall go to the notebook environment. We shall now look at the implementation of self-attention in Python. We shall use the basic libraries NumPy and math library. We are not going to use any fancy libraries such as PyTorch or TensorFlow. But before moving ahead, I wanted to show you one thing I forgot in the earlier part. The encoder layer, basically this encoder layer consists of two sublayers. One is the multi-head self-attention and other is the feed-forward layer. Okay, remember this when you're talking about the architecture. These are the two important sublayers within the encoder layer. Okay, let us go ahead and now run this. Our sequence is data science learning is fun. This has 5 different words. Currently we are considering each token as one word. Okay, but if we know from our Hugging Face understanding, from our tokenizer understanding of Hugging Face, that a token could be less than a word as well, basically a sub token. Okay, we are taking L, the sequence length is 5 here. DV and DK we are assuming them to be 8. This could vary. Okay, and here we are randomly initializing our matrices. In the real scenario, these are generated from say V matrix is generated from WV, which is a learned matrix, and the input sequence, input embedding basically. Okay, similarly they are generated from WQ and input embedding. Okay, to keep things simple, we are taking randomly initializing them. Let me show the output. So basically we have an input which is having L cross DK, so that is 5 cross 8. Okay, if we print it, let me just print and show you. Q dot size, sorry, 5 comma 8. Okay, now the self attention formula that we know is softmax of Q KT K transpose, and then we scale it using root of DK, basically here root of 8, and then we do a matrix multiplication with the value vector. So first we have to perform the matrix multiplication between Q, that is our query matrix, and our key matrix. Okay, we get the corresponding output which is of the shape L comma L, 5 comma 5. You see the variance, let me show you the variance. The variance of Q matrix, K matrix is nearly 1.35, right? And the variance of V matrix is also 1.25. However, the variance of the matrix multiplication of Q and KT is 6.24, which is much higher in scale, and therefore we rescale them back using root of DK in order to bring them to the same scale. Let me show you again. So scaled SA dot var, you see it is nearly in the same range now, right? That is why scaling is important. Now the optional part, is basically the masking. This masking is used in decoder only, we don't use in encoders. In decoders, basically we process the context in sequential fashion, unlike encoders where we pass the entire context, entire sequence in order to learn the context. Okay, so therefore for masking what we do, we make all the right diagonal, all the elements on the right diagonal as zeros, because we want to consider them in a sequential fashion. First this, then these two, then 3, then 4, then 5, like this. Okay. Okay, now we are applying a softmax. Now if you have to apply this masking, you just do scaled. This is the operation that needs to be done when masking is applied. Scaled NA plus mask, sorry, scaled SA. Okay, just a second. Okay, now softmax operation. So softmax operation, we have the formulation for softmax. We apply the softmax on the scaled SA, we get the attention output. Okay, next we perform the matrix multiplication, np.matmul attention comma v. Now the final, this is the output of our self attention, and the shape of this will be okay, just give me a second. new v dot shape. You see the shape of this is L comma dv, which is 5 comma 8. So this is how very simply we are able to implement a self attention mechanism in Python. I'll share this notebook as well with you so that you can go around and make your own implementations. You can use torch as well, but here we did not require it. So hope this, with this you learned something new. If you like the content, make sure to give it a thumbs up. See you in the next lecture. Have a nice day. Bye bye. Jai Hind.